Welcome back to the Explainer. Now that we've got the basic mechanics down from Section 5.1, today we're zooming in exclusively on Section 5.2, frequency selectivity on the basilar membrane. We are going to explore what is honestly one of the most miraculous mechanisms inside the human body. For the longest time, we thought of the ear as just a simple microphone, kind of like a passive receiver that just vibrated along with whatever sound waves hit it. But today, we'll see how the basilar membrane, which is deeply embedded inside your inner ear's cochlea, actually acts as a dynamic, living frequency analyzer. It's constantly adapting, compressing, and shifting. This is the exact mechanism that gives us our incredible sense of hearing, letting us pick up a faint whisper in a totally quiet room, while also handling the roar of a stadium without just completely overloading our senses.
Here is our roadmap for today. Number 1, recent measurements. Number 2, ringing. And number 3, nonlinearity. Let's get right into it. Section 1, recent measurements. Observing the living cochlea.
To really grasp modern frequency selectivity, we've got to look at how recent measurements completely flipped our understanding of the cochlea's delicate tuning. Early experiments, like those pioneered by von Basilar back in the 1960s, actually used sound levels as high as 140 decibels just to get the membrane to move enough so they could measure it. To put that into perspective, 140 decibels is literally like standing right next to a firing jet engine. That kind of intense acoustic trauma practically deafened the ears they were studying right on the spot, which led researchers to measure this broad, dead, passive response. But modern techniques, they are vastly different, incredibly gentle, and honestly just brilliantly inventive. Today, researchers perform these delicate experiments on anesthetized chinchillas or guinea pigs. They open the cochlea ever so slightly, drop a microscopic reflective glass bead right onto the living tissue of the membrane, and then literally bounce a laser beam off that tiny bead. This lets them measure the exact velocity and displacement of a single living place on the membrane while playing a sound. When you look at the data, you can see the actual shapes of the biological filters in our ears. Take a single spot on a chinchilla's basilar membrane, specifically one tuned to 10 kilohertz. The closer a tone is to that 10 kilohertz sweet spot, the faster the membrane vibrates. It acts exactly like a finely tuned bandpass filter. Think of it like tuning an old-school classic car radio dial. When you're slowly turning that dial, you're trying to lot onto one specific station, right? The filter only lets that one specific frequency through loud and clear, while actively blocking out the static of the stations immediately above and below it. Well, our living membrane is doing the exact same thing with acoustic frequencies. And just to give you a true sense of the microscopic scale we are dealing with here, on this specific measurement scale, 0 decibels represents a velocity of exactly 1/1,000,000th of a meter per second. That is a fraction of the width of a single human cell. It's an absolutely astonishing microscopic flutter. Yet, our brain takes this infinitesimally tiny, silent mechanical vibration and decodes it instantly into the rich, emotional texture of a soaring violin or the airy breath of a flute. It's a total biological marvel that this tiny movement translates directly into our daily experience of music and conversation. But here's the tricky part, because the ear acts like a moving target, constantly adjusting its sensitivity based on loud environments. Auditory scientists had to find a reliable, stable baseline to measure against. So they strictly define the characteristic frequency of a specific place on the membrane based on its response to quiet, low-level sounds. A whisper is basically the truest test of the membrane's resting, uncompressed state. When the environment is super quiet, the ear's filter is at its absolute sharpest and most precise. That point of maximum sensitivity, where the faintest possible sound causes the most vibration, becomes the definitive characteristic frequency for that exact spot on the biological map. Now, if we map this out geographically along the cochlea, we see two very different operational modes. The base of the cochlea handles high frequencies and has much wider absolute bandwidths. But down at the apex, which handles the low frequencies, the absolute bandwidths in hertz are a lot narrower. To break this down without getting bogged down in acoustic math, just imagine a piano keyboard. Absolute bandwidth is like measuring how many physical keys are vibrating. Proportional bandwidth is measuring the percentage of the whole keyboard that's vibrating. Down at the apex, dealing with those low notes, only a very narrow set of physical keys vibrate. That's the absolute bandwidth, even though proportionally, it's a bigger chunk of the low-end spectrum. It's a highly specialized graded system from one end of the ear to the other.
Moving on to Section 2, ringing, the physics in time.
Imagine a sudden, sharp sound, maybe a hand clap or a snapping twig, hitting your ear. A click like that isn't just a single note.
It's a broadband burst of acoustic energy that strikes the eardrum all at once, sending a literal shockwave through the fluid of your inner ear. So what actually happens inside your ear in the milliseconds that follow? Does the tissue just snap back to zero immediately, completely deadened, or does it reverberate and echo like a struck bell? Well, at the base of the cochlea, which handles those high characteristic frequencies like 4,000 hertz and features those wide absolute bandwidths we just talked about, a sudden click causes the membrane to vibrate very briefly. It rings out for maybe a millisecond or so before settling completely. This rapid, almost instantaneous damping is exactly why high-pitched clicks, snaps, and ticks sound so incredibly sharp and distinct to us in the real world. The physical tissue stops moving almost immediately after the sound stops. But the contrast is mind-blowing as we move further down toward the apex of the cochlea where the lower frequencies live. At 1,000 hertz, and even more so at 250 hertz, the membrane behaves totally differently. Here, the impulse causes a long, sustained wave. The membrane actually continues to ring and vibrate for tens of milliseconds after the click has already ended. Now, tens of milliseconds might sound lightning fast to us, but in the microscopic world of the ear, that is an absolute eternity. It's the biological equivalent of hearing the deep, resonant boom of a massive bass drum sustaining in a concert hall versus the sharp, immediate tick of a snare drum. So it all boils down to a really elegant, fundamental physical rule of the universe. Narrowly tuned absolute bandwidths, like those at the apex, ring for a long time and produce an echo. On the flip side, broadly tuned filters, like those at the base, stop ringing almost immediately and produce a quick stop. Our cochlea uses this exact physical rule to map both time and pitch simultaneously along a single, continuous spiral of living tissue. Pretty amazing, right? Which brings us to Section 3, Nonlinearity, the big reveal. The source material puts it pretty bluntly. The response of the base of the basilar membrane is highly nonlinear. In a basic linear system, like your standard volume knob on a stereo, turning the input up from a 2 to a 4 gives you exactly twice the output. The shape of the sound never changes, it just gets uniformly louder. But your healthy cochlea, it defies this completely. It is an active mechanism that literally pushes back against the sound. It changes its own filter characteristics, altering its shape and its physical behavior based entirely on the sound level it's currently experiencing. This creates this bizarre, incredible mechanical effect we call a basal ward shift. Here's how wild it gets. At a whisper quiet volume, a pure tone perfectly hits its characteristic frequency spot. But as the volume in the room increases, the best frequency of that exact spot actually shifts downward by about half an octave. Imagine hitting a key on a piano really hard, and the physical string that vibrates inside the piano magically shifts its preferred resonance down halfway to the next note. Because of this, the peak of the physical traveling wave literally slides physically down toward the base of the cochlea as the sound gets louder. In plain terms, your basilar membrane acts as a highly advanced dynamic shock absorber. The system is heavily compressive at moderate to high volumes. A massive 10 decibel jump in the room you are standing in might only translate to a tiny 5 decibel increase in the actual physical vibration inside the membrane itself. The ear is literally protecting itself from damage in real time. This is the exact mechanism that lets you safely walk down a screaming, noisy city street with sirens blaring without your ears blowing out, while still remaining magically hypersensitive to the quietest rustle of leaves when you step into a silent park. And this is a massive aha moment for understanding real-world hearing loss. The live, healthy ear is highly sensitive. It actively compresses the loud sound, forming a shallow, dynamically curved response. But the dead or unhealthy ear, it simply reacts in a straight, linear line and requires vastly more input volume just to move the membrane at all. This is exactly why people with hearing loss don't just need things made louder. A basic linear hearing aid just turns up the volume on everything. But because their biological compressor is broken, making a crowded room uniformly louder just creates an unbearable wall of noise. Without this active living nonlinearity, we totally lose that delicate ability to pick out a single conversation at a noisy cocktail party. To sum up this little miracle, a healthy ear safely broadens its tuning and physically shifts its peaks at high levels to compress incoming sound and protect the system. But if the ear's physiological state deteriorates, say from age, trauma, or disease, it loses that magic nonlinear compression entirely. It permanently reverts to a dull, insensitive, linear state that requires massive amounts of sheer acoustic force to register any signal at all. Since this living, shifting, non-linear instrument sets the absolute physical limit on what frequencies we can hear, it leaves us with one heck of a puzzle. Think about it. If the physical map of sound inside our ear is constantly changing shape, compressing its data, and sliding its peaks around based purely on how loud the room happens to be, how on earth does the rest of the nervous system decode this constantly shifting map to let us hear a stable, clear world? We're going to tackle that exact puzzle as we move into sections 5.3 through 5.6 in our upcoming explainers. Catch you then.